Straight ahead is the Rockin' World of Geology Program 2. We have a rip-roaring, rock'em sock'em show in store for you. First, we'll take a look at minerals. You'll learn all the basics, starting with the burning question, what is a mineral? Then we'll cover magma and intrusive rocks. You'll learn about igneous rocks, plutons, and magma. Magma. We'll even settle that age-old question, what's the difference between lava and magma?
It's time for our pop quiz. Here's the question. Which of the following is not a physical property of minerals? A, luster. B, cleavage. C, custard. D, hardness. Stay tuned and we'll give you the answer after the program.
The Standard Deviants present The Rockin' World of Geology.
Starring Brad Aldous, Galila Azrez, Herschel Bliefeld, Jeremy Clavens, Tessa Monroe, Dana Rubinson, Gabrielle Smith, Malcolm Smith, Shannon Ward, and Jazz Maston.
Section C, Minerals.
Rocks are made of minerals. So to understand rocks, we have to understand minerals. A mineral is an inorganic solid with a unique chemical composition and crystalline structure that's found in nature. Does it sound like we're about to talk chemistry instead of geology? Well, we are, and we'll tell you more about inorganic crystalline solids in a minute.
Oh, what an unexpected delight!
Fact is, a lot of geology is based on chemistry. We're going to go over a little chemistry here, but if you need to learn more about atoms and ions, valence shells, bonds, and all that stuff, check out the supercharged world of chemistry.
It's the chemistry and crystalline structure of the minerals, the way elements interact and bond that give minerals their characteristic shapes, color, and hardness. Chemical properties of elements and bonds dictate how minerals are formed. The abundance of certain elements in the earth, along with the chemical properties of those elements, determine which minerals are more prevalent than others.
Remember we defined minerals as inorganic crystalline solids? You have to know a little chemistry to know what that means. An inorganic material is neither animal nor vegetable. It is material that does not arise from life processes. Crystalline solids are made up of atoms bonded in a three-dimensional geometric pattern.
For example, the mineral halite, also known as sodium chloride, or NaCl, has a crystal structure. Note the three-dimensional geometric structure formed by the bonded atoms.
Solids which don't have crystal structures are called amorphous.
A what?
Amorphous. It's not a what, it's an adjective. It means without form. The elements making up amorphous solids don't form geometric structures like the ones in crystalline solids. Glass and amber are amorphous solids. So, by definition, even naturally occurring glass is not a mineral.
What's an adjective?
It's Billy, the amorphous boy.
Hey, Mom, can I go out and play?
Why, sure, Billy.
Sometimes minerals with the same chemical composition can have different crystal structures depending on how the elements bond to each other. For example, diamonds and graphite are both made of only carbon. You know what graphite is, right? It's plain old pencil lead. Diamonds are nothing like pencil lead. So how can it be that they have the same exact chemical composition?
Here's the difference between diamonds and graphite. The crystal structure of diamonds is quite different from the crystal structure of graphite. It's the way the carbon bonds to itself that makes diamonds very hard and graphite very soft. Diamonds and graphite are called polymorphs, poly meaning many, and morphs meaning shapes. Polymorphs are minerals with the same chemical formula but different crystal structures.
Isomorphs are the opposite of polymorphs. Iso means same, and morphs means shapes. So isomorphs are two minerals which have the same crystal structure but different chemical compositions. Galena and halite are examples of isomorphs. Both have a crystal structure that forms a perfect six-sided cube, but galena is composed of lead sulfide and halite is composed of sodium chloride.
The most common elements in the Earth's crust are oxygen and silicon. The most common rock-building minerals are silicates, minerals composed of oxygen and silicon. The silicate ion, which is made up of one silicon atom and 4 oxygen atoms, is the basic building block of these minerals.
Quartz is composed entirely of silicon and oxygen that bind together in a three-dimensional network.
May the quartz be with you.
We would show you what this network looks like, but we can't show it accurately on your two-dimensional TV screen. Just remember that it's quartz's tight bonding pattern that makes it so hard.
In some minerals, the silicate groups are not as tightly bound to one another, and the result is a mineral that is soft and breaks apart easily. For example, minerals called micas are composed of two-dimensional sheets of silicate ions, but because the sheets are not tightly bound to one another, the mineral crumbles readily.
The physical properties of minerals are dictated by the chemical and physical processes that formed them. In fact, minerals are identified and classified by their measurable physical properties, including hardness, cleavage, fracture, luster, and color. We'll elaborate on all these physical properties, so pay attention, because you'll probably see this stuff on your test.
The first measurable physical property that we use to identify and classify minerals is hardness. A mineral's hardness is its ability to resist abrasion. Friedrich Mohs devised a hardness scale that we use to measure and compare the hardness of minerals.
Nobody knows old Friedrich Mohs. He used to take stones and put them up his nose.
Here's the Mohs hardness scale. The Mohs hardness scale rates 10 minerals from diamond, the hardest mineral, to talc, a very soft mineral. Remember, hardness refers to the mineral's ability to resist abrasion. Quartz will scratch calcite because it is harder than calcite, but calcite won't scratch quartz. Calcite will scratch gypsum, however, because gypsum is softer than calcite. See how it works?
They never seem to fit right.
The next physical property we use to identify and classify minerals is called cleavage. Cleavage is the way that crystalline minerals split or break across planar surfaces. Where and how minerals split or cleave depends on the strength and arrangement of the bonds in their crystal structure.
Enough about cleavage. Fracture, another physical property, is a lot like cleavage. But a fracture is a break along an uneven surface. It's also what happens to your leg when a cow sits on you, but that's not important right now. Remember, cleavage occurs along planar surfaces. Any mineral will fracture if enough pressure is applied to it.
The next physical property of minerals is luster. Luster refers to the way that minerals reflect light. There are two types of luster, metallic and non-metallic. A mineral with metallic luster looks like a metal when light reflects off of it. Galena, for example, is composed of lead sulfide and it has a metallic luster. Minerals with non-metallic luster like this orthoclase, may look glassy, greasy, waxy, brilliant, or dull and earthy. To help you out, let's compare metallic and non-metallic people. This man is metallic. As you can see, he looks like a metal, and light reflects off him. Freak. This woman, however, is non-metallic. Notice the glassy eyes, waxy color, and overall earthy appearance. Tree hugger. Metallic, non-metallic.
Color is the final physical property we'll discuss. Often minerals of the same type will be different colors, but this is not always the case.
For example, fluorite can be purple, green, blue, or yellow, but many minerals, such as pyrite, never vary in color. Pyrite is always brassy yellow.
Here's a summary of what we just learned. A mineral is an inorganic crystalline solid with a unique chemical composition that's found in nature. Solid materials which lack crystal structures are called amorphous solids. Polymorphs are minerals with the same chemical formula but different crystal structures, such as diamonds and graphite. Isomorphs are the opposite of polymorphs. They are two minerals which have the same crystal structure but different chemical compositions, such as galena and halite. We describe minerals with measurable physical properties including hardness, the ability to resist abrasion, cleavage, the way that crystalline minerals split or break along planar surfaces, fracture, the way minerals break along uneven surfaces, luster, the way minerals reflect light, and color. Specimens of the same mineral are often, but not always, different colors.
Section D, magmas and intrusive rocks.
Magma is the name for molten rock below the Earth's surface. It's a siliceous liquid which has a chemical composition like that of the Earth's crust. Really, it's just liquid Earth's crust.
What does siliceous mean?
Okay, siliceous, that's a good question. Siliceous just means that the magma contains silica, the common compound we spoke of earlier, which is composed of silicon and oxygen atoms.
So magma is liquid Earth crust. And it's a siliceous liquid because it contains silica. So what's the difference between magma and lava?
Okay, lava is just magma that's made its way up through the Earth's crust to the surface. Once the magma shoots out of a volcano or oozes out of a crack of some sort, it's called lava. Now, like we mentioned earlier, rocks that form from cooling magma or lava are called igneous rocks. Now, igneous is a general term that describes any rocks that form from magma or the accumulation of the stuff like lava and ash that shoots or oozes out of a volcano. Now, there are two broad categories of igneous rock: the rock that forms from lava on the surface of the Earth and the rock that forms from magma below the surface of the Earth. We'll tell you about these broad categories first, then we'll go into details on specific types of igneous rock.
The first category is extrusive igneous rock. Extrusive igneous rocks form from lava, so they cool and crystallize on the Earth's surface. Extrusive comes from the word extrude, to force or push out. Remember EX for out. Extrusive igneous rock has exited the surface of the Earth. Extrusive igneous rock is also called volcanic igneous rock.
Sometimes magma doesn't make it out of the crust, but it cools and forms solid rock anyway. Magma that cools and crystallizes within the Earth's crust forms the second type of igneous rock, intrusive igneous rock.
It's pretty easy to remember what intrusive igneous rocks are because the word intrusive will remind you that these rocks formed from magma that cooled inside the Earth's crust. Intrusive rocks are inside. Intrusive igneous rock is also called plutonic igneous rock because it forms plutons.
Plutons are just bodies of intrusive igneous rock. Magma cools beneath the Earth's surface, and the lump of solid igneous rock that forms is called a pluton. Simple as that. There are two kinds of plutons, concordant plutons and discordant plutons.
Concordant plutons lie parallel to the layers of rock that were already there when the pluton formed. The pre-existing rock is often called the country rock. When you think of concordant, think of the Concorde airplane that flies parallel to the ground. Concordant plutons lie parallel to the existing or country rock.
Discordant plutons cut across the layers of existing country rock. Dis is a prefix meaning to do the opposite of. Discordant plutons diss the country rock. They do their own thing and go their own way.
If plutons are intrusive igneous rocks that form beneath the Earth's surface, how can we see one cutting through a bed of country rock? I mean, wouldn't the pluton be buried?
Well, not necessarily. See, what happens is even though the pluton formed beneath the surface, the beds of country rock around and overlying the pluton may erode away to expose the pluton and the bed of rock it's cutting through. Now, we'll talk more about erosion and weathering later on.
I'm so relieved.
The largest plutons are called batholiths. By definition, batholiths must be at least 100 kilometers squared in size. That's 61 square miles. Think of it, a giant igneous rock that covers 61 or more square miles. You could build a city on a batholith.
I said batholith, not bathtub.
Discordant plutons that are smaller than 100 kilometers squared are called stocks. Many plutons that are called stocks, however, are actually just the exposed part of much larger plutons.
Hey! Get with it, you geologists!
The amount of time it takes the magma to cool and crystallize affects the texture of the igneous rock it forms. When magma cools slowly, it allows more time for crystals to form, so you end up with a rock with larger crystals. On the other hand, when magma is quenched quickly and the crystals don't have a lot of time to grow, you get a rock with small crystals, a fine-grained rock.
The texture of an igneous rock will give you a clue about the environment in which the rock formed. An intrusive rock, which cools and turns into rock below the Earth's surface, will generally cool slowly. Slower cooling means bigger crystals, so intrusive igneous rocks frequently have large crystals and a coarse texture. Extrusive rocks, which cool on the surface of the Earth, cool quickly, resulting in a fine-grained rock with smaller crystals. Sometimes lava flowing from a volcano cools so quickly that there's no time for crystals to form at all. When this happens, a volcanic glass, like obsidian, forms.
Sometimes magma starts cooling below the Earth's surface. Then it gets forced through the crust and finishes its cooling above the ground. Now, a rock that starts forming beneath the surface and finishes forming on the surface is called a porphyry. All right, now, porphyries have what's called porphyritic texture.
Pork arthritic texture? That sounds like it would really upset my stomach.
No. Porphyritic. Okay, porphyritic.
I've never eaten that.
Porphyritic texture is characterized by larger crystals called phenocrysts, surrounded by a fine-grained matrix of little crystals that form after the magma starts cooling quickly on the surface. Like we said earlier, igneous rocks are any rocks that form from magma. But not all magma is composed of the same stuff, so not all igneous rocks are the same. Magmas are divided into 4 categories based on their chemical composition: felsic, intermediate, mafic, and ultramafic. Each type of magma yields different types of igneous rocks.
Silica is a compound composed of oxygen and silicon atoms. Magma rich in silica is called felsic magma. Besides silica, felsic magma contains a considerable amount of sodium, potassium, and aluminum. Felsic magma cools to form igneous rocks such as granite. Magma poorer in silica is called mafic magma. Mafic magma and the igneous rock it forms are rich in minerals containing iron and magnesium. Mafic minerals composed largely of iron and magnesium are called ferromagnesian minerals. Pyroxene and amphibole are ferromagnesian minerals. As you might expect, intermediate magma has a mineral composition that's richer in silica than mafic magma and poorer in silica than felsic magma. Finally, ultramafic rocks are even poorer in silica and richer in magnesium and iron than mafic magma.
The color of rocks and minerals reflects their chemical composition. Felsic minerals tend to be light, and mafic and ultramafic minerals tend to be dark.
For example, granite, which is felsic in composition, is a light-colored rock. Basalt is mafic, and it has the characteristic dark color of a mafic rock.
Another way to tell the difference between felsic, mafic, and ultramafic rocks is by tasting them.
A is mafic. B, felsic. And C is ultramafic.
Well, there you have it, folks.
Now listen closely, because I'm going to explain a process that's a little tricky.
As magma cools, the uncoordinated ions within it organize themselves into minerals. You can get a bunch of different kinds of minerals from magma because magmas contain various mineral-forming elements. The different types of minerals that form from magma form in a specific sequence according to the freezing temperature of the mineral. Now, don't let the term freezing temperature mislead you. A mineral's freezing temperature may not be especially cold. The freezing temperature is just the temperature at which a liquid becomes a solid. Some minerals become solid when they're still pretty warm, and others have to get quite a bit cooler before they solidify. That's why we say they solidify in a specific sequence. The minerals with the higher freezing temperatures solidify out of the magma first, and the ones that need a lower temperature to solidify form later.
So like we said, magmas can form igneous rocks with a range of chemical composition. But here's the crazy thing. All these types of igneous rocks and minerals can form from a single mafic magma. When these different minerals come out of one type of magma, it's called magmatic differentiation.
Okay, wait a minute. Now, earlier we said that certain types of magma cool to form certain types of minerals. Like, for example, felsic magma forms granite. How can you get all different types of igneous rocks from a single magma?
Okay. Both felsic and mafic magmas are liquids, which are composed largely of the elements oxygen, silicon, and aluminum. And each type also contains sodium, potassium, and calcium as well. Each type also has at least some magnesium and iron. Now understand that. Just chew on it up and swallow it. Here comes the difference between the two types of magmas. Mafic magma, in comparison to felsic magma, has a lot more magnesium and iron and a lot less aluminum, potassium, and sodium. Ultramafic magma has even more magnesium and iron and even less aluminum, potassium, and sodium. Okay. Felsic magma, in comparison to mafic magma, has less magnesium and iron and a lot more aluminum, potassium, and sodium.
Okay, so felsic and mafic magmas are composed of pretty much the same elements, but in different proportions.
Right. Both magmas can form some quantity of the various minerals. How much of each type of mineral the magma can form depends on how much of the necessary elements the magma contains. Mafic magma can form a small quantity of the minerals that contain aluminum, potassium, and sodium. Ultramafic magma will form an even smaller quantity of these minerals because it has even less of the necessary elements. Felsic magma, on the other hand, can form a larger quantity of minerals containing aluminum, potassium, and sodium because it contains more of those elements than mafic magma.
How does magmatic differentiation happen? In 1928, a guy named N.L. Bowen came up with a theory to explain it. Here's a picture of Bowen. No, that's the cookie elf. Anyway, based on Bowen's observations and experiments, Bowen proposed a general scheme that explains how felsic minerals might crystallize from a mafic magma. His scheme is called Bowen's reaction series.
Here's the basis for Bowen's reaction series. As magma cools, not all types of minerals crystallize simultaneously. Remember we talked about freezing temperatures earlier? The minerals with higher freezing temperatures crystallize first, and then, at successively lower temperatures, other minerals crystallize.
Can you explain magmatic differentiation?
It's the polarity of the antithesis of one ion excruciating its differential force on another.
Well, I believe that might be right.
Etched in stone. Okay, let's etch. Plutons are people from the planet Pluto. Oh no, that doesn't look right. Let me try that one again. New stone. Plutons are lumps of solid igneous rock beneath the Earth's surface. Well, hi diddly ho, that's much, much better. Etched in stone. It's time for the answer to the pop quiz. We asked you to identify which of the following is not a physical property of minerals. The correct answer is C. Custard. Luster, cleavage, and hardness are physical properties that geologists use to classify minerals, while custard is a delicious dessert treat.